Here's the definition of row echelon, and we'll identify some of these other definitions that are floating around and some that you don't see yet. Remember that all the rows that are all zeros go in the bottom, and every other row will have what's called a leading entry, and that leading entry is going to be set up so that you have like a staircase looking system or matrix. We talked about row operations. One row operation is to switch the order of two rows. Another one is to multiply one of the rows by something. We saw that in our very simple example of two systems, or two equations and two unknown systems. And then one that's the last one is the most popular one, where you take a row, multiply it by something, and then add it to another row, and then replace that row. Probably should have switched the order of this. It should have been KRJ plus RI, and then that replaces RI. So the process of doing these row operations is called row reduction. You're reducing this so that it's an echelon form, row by row. And then a couple of one definition and one theorem here to get us started is that if you have two matrices that can reduce, or that can be converted one from the other, that can be converted so that you're using the row operations that are called row equivalent. And then the last one is a theorem that says if you have anything that can be reduced into the same row echelon form, then all those matrices are row equivalent. Okay, so we'll take these definitions and then some, and then apply it to, or I'll highlight where they pop up when we do an example. All right. This might have been in the last slide. If it's not, this is the actual process that we will take to try to solve for a system. So what we do is we look at a system of linear equations and we translate that into a matrix. And then we're going to take a series of row operations so that we can reduce it into a row echelon form. And once it's in row echelon form, we're going to back solve it, go backwards to try to solve for our system. Okay? So that's the steps, the three simple steps to solve simple. So part 2 is where you do all the work, and part 3 is the little algebra part that you finish off to complete your problem. Let's do this problem. This is number 26 from your textbook, and let's see, maybe I'll go across first and then go down. So some of these could take a while, some of them might be easy enough to do, and some might take a little bit more work. So the first step is to write it in matrix form, the augmented matrix. So we have x, y, z are your variables. 1x, 2y, 0z is equal to -1. 2x, 1y, 1z is equal to +1. -1x, +1y, minus 1z is equal to -1. So this is your augmented matrix. Now you want this in row echelon form, so what you want to do is you want to make start creating zeros down here. And so let's do this as our first step. This is where we start doing our elementary row operations now. I'm going to take row 1 and just not do anything with it. Multiply it by 1 if you want to think about it that way. Add it to row 3. If I add row 1 to row 3, and I'm noticing the first terms or the first elements in those row vectors, I see that that's 1 minus 1, that's going to be 0. That's what I want. And so I'm going to replace, with my result here, I'm going to replace row 3. So row 1 plus row 3 is going to replace row 3. So if I'm going to replace row 3, I didn't do anything with rows 1 and 2, so they will remain the same. So this is where I do my work. 1 minus 1 is 0. 2 plus 1 is 3. 0 minus 1 is negative 1. Negative 1 minus 1 is negative 2. Okay? All right, now in terms of the definition, according to the definition, when we go from one matrix to another via a row operation, that means these two matrices are row equivalent. So that's just to remind you of the definition that we just talked about, and this is how it gets applied. All right, our next step, maybe I'll keep eliminating, because part of row echelon form is that if I have a leading term on one row, anything else below it will be zeros. So I'm going to knock off the second first element, the second row. And so that's a 2 there. I want to take my row 1 and multiply that by negative 2. And then I'll add that to row 2. And then I will then replace row 2. Yeah? How do you know? I could have replaced row 1, but if I would have replaced row 1, that would have gave me a 0 up on top, and that's not necessarily row echelon. I could have done that and then later on switch, because that's another elementary row operation. Yeah, I could do a lot of different things. But the bottom line is I want this to be a row echelon form, 0s in the bottom left corner of your matrix. So, so I'm going to start by taking a look at the first column and knocking all the zeros out, or knocking out all the numbers. All right. So I'm looking at this 2 over here to disappear. Maybe I'll look at this one right here. Oh yeah, I need to look at this one. I didn't do anything with the first row, and I didn't do anything with the third row. So what happened to the second row? I multiplied the first one by negative 2 and added it to the second, and so that's negative 2 plus 2 is 0. Negative 2 times 2 is negative 4, plus 1 is negative 3. Negative 2, there's nothing there, plus 1 is 1. Negative 2. Yeah, is that right? That's right, right? Oh, okay. Okay, so that's there, and then I multiply the augmented part by 2, or negative 2, so that becomes positive 2, plus 1 is positive 3. Okay. I could, probably. Maybe not rows 2 and 3, but maybe get rid. So right now, I'm almost there in terms of my row echelon form. I just want this last one to be 0. So it looks like I can add row 2 with row 3. So let's do that. So I'm going to take row 2. And I'm not going to multiply that by anything because they already are opposites. And I'll just add it to row 3. And I will replace row 3. So I'm replacing row 3, which means row 1 and row 2 stay the same. And so what happens to row 3? This is already 0, and part of the process of doing this is that you want to eliminate the first column, the 0, make the first column 0 first. And then what happens there is that you can then start working downward in your step. So here I just add minus 3 plus 3 is 0. I have a 1 plus negative 1, that's also 0. And then I have a 3 plus 2 is negative, positive 1. What? I don't know. I was just following the instructions here. And now what do we have? All right, well, I think this is in row echelon form. So according to the instructions, we'll use back substitution to write it. So before we do use back substitution, we need to rewrite this back into our system. So it looks like nothing happened with the first equation here. X plus 2y plus 0 is equal to negative 1. My second equation is minus 3y plus z is equal to 3, so that changed. And then my last equation is 0 is equal to 1. Okay, so here we have a problem. Okay, so what we have here is before we talk about our problem, let's take a look at these matrices. So this is the reduced form matrix. It's in row echelon form. According to the definitions in the theorems, these are all equivalent, row equivalent matrices. The first one is row equivalent with the second one, which is row equivalent with the third one, which is row equivalent with this one. So these are all row equivalent matrices, according to the definition. What else? Elementary row operations, row reduction, row equivalent, row echelon, leading entries. So if we take a look at this, green, these are the leading entries for your matrix. Okay? All right, now let's deal with the problem. This isn't the first time that we got a contradiction, is it? That means what? Not that they're not equivalent. Okay, now, so this is yeah, so the trickier part is that this is in 3D. Now, we still have a chance of visualizing this because it's in 3 dimensions. And if we add another variable, then we're just out of luck and it's 4 dimensions. We can't visualize it. But here in this case, we're still in 3D, so we can visualize it, and we will. We'll take a look at the graph of these things and see what's really happening. But what happens when you come up with something like this, where you have, now these are planes. These are 3 planes. Remember when I told you to throw a couple of sticks and make it land on the floor? This time, throw a couple of planes and make it stay in space. Whoa. And then, so you have a couple of pieces of paper that won't bend, throw them in space, and then make it freeze in space, and then make the papers go infinitely long forever. What could possibly happen? What? They can intersect. Now, the really rare case is that they intersect at exactly 1 point. All 3 of those planes in space will intersect at 1 point. if that was the case, then we would have gotten a solution here. So another rare case might be these three would intersect in exactly one line. Right? And the binding is where they would intersect. So if they intersected in one line, then we would still find a solution somehow. We got a contradiction. Where are the planes? I wish I had a hologram. I want a hologram. I want a hologram for Christmas, so if anybody wants to give me one. What? Well, if they were on top of each other, we'll definitely remember if they were exactly the same line, we got a what's that word called? That philosophy word that I made up? Tautology. You get a tautology for that. If they were exactly all the same lines, you're going to get true statements all over the place here, and we got a contradiction. So the only other option is that these planes are parallel, or maybe two of them are parallel, and so two of them don't touch, so then something happens. Okay? All right. Since we do still have a chance of visualizing this, and we do have the capabilities to actually visualize this, let's do that and see how these planes look like. I'm going to start with the bottom one, because I think I need three variables for my first equation. So minus x plus y minus z is equal to negative 1. 2x plus y plus z is equal to positive 1, and x plus 2y, there's no z's, is equal to negative 1. Well, I guess they're not all parallel, but so they touch, two of them intersect, then the other two intersect, and so there's no parallel planes here, but these three planes doesn't look like they intersect in one line at the same time or at exactly one point at the same time. So, can you guys see? Is it too dark? So it's one of those cases where, let's see if we could draw it. So there's one plane, and here's the other plane. So if it was just two of them, they would be intersecting at a line somewhere. But then the third one, uh-oh. Now I got all messed up. Yeah, so basically it would look like a tent. Maybe I should just draw a tent. So here's one plane, here's another plane, and then the bottom one's the other plane. And so it looks like if you just take two of them at a time, they would intersect, but if you take all three of them, they don't intersect, so there's your contradiction. All three intersect somewhere, either a point or a line or something. Which, if you throw three pieces of paper up in the air and freeze them and then extend them, it's very rare that you get all three of those planes to intersect. Just like when you throw two sticks and make it land on the floor, it's more common that they would intersect at exactly one point than for them to be parallel or actually land on top of each other. But we're not talking about probability, so let's not worry about it. Okay, so that's this is one example. Any questions? So the process is what we're studying right now, the row echelon form process. And then once we get to the result, we can analyze and talk about the result and see what's going on. Yeah?
So what about row echelon form? It has to have one less zero in every line.
Yes, it has to have one less zero, because if there's not one less zero, then you can still get rid of it. So at this point, it wasn't row echelon yet, but you can still get rid of the bottom one. So there's always a chance to get rid of the bottom one. To get rid of this one.
The next one, so get rid of
Up here? If you want. Maybe. Vague questions. I mean, vague answers. Good questions, vague answers. Yeah, it's. We'll see another definition. The other definition is called reduced row echelon form, which makes everything else 0, and then you can immediately see your answer that you're looking for. But here we're just doing the regular. Let's do one more. There's we did number 26, and there's a few more to choose from. There's 28, which is 4 variables, and there's 29, which is 2 variables. So I consider them both interesting, but I'm only going to do one. Which one do you guys want to see? What? All right, there's a vote for 28, so let's do 28. And you guys can figure out 29. Let's do 28. So let's first write this into our augmented matrix. And it looks like in order, my first variable is W and then X, Y, Z. So in order, my columns would be 3, 3, 1, 0, and then the augmented part is 1. And my next row is 2, 1, 1, 1, and then another 1, and then 2, 3, 1, negative 1, and 2. Yeah. Row 3? We could do that. So we'll take row 2, multiply it by negative 1, and then add it to row 3, and then replace row 3. So that will get row 3 to be, the first element in row 3 would be 0. So 3, 3, 1, 0, 1. I didn't change row 2. I'm going to change row 3. So row 2 stays the same. And then now this is going to be 0. So multiply by negative 1. That's negative 1 plus 3 is 2. Negative 1 plus 1 is 0. Negative 1, negative 2. And negative 1 plus 2 is positive 1. Say it again?
So you take row 2 times by negative 1 and add it to itself.
You can't add it to itself. You can multiply this by negative 2, and then that would make it 4, 2, 2, 2, 2. So that's another row operation, but you can't add it to itself. That would be like suicide, right? That's everything. Everything would be gone. Well, maybe that wasn't a funny joke. All right, so now I think we're going to have to get stuck with fractions here, so let's just suck it up and deal with it. So I need to get this 2 out of the way, and to do that, I'm looking at this 3 over here, and so I need to do something with 3. I need to multiply row 1 by something, and then do something to that, and then add it to row 2, so I can replace row 2, and the 2/3 negative maybe. So the 3 would cancel. This would give you a 2, and then a negative would cancel it. So negative 2/3 would do. I didn't change row 1. I didn't change row 3. All right, so this is my work now. So this is going to be 0. That was the whole setup. 3 times negative 2/3 will give me a negative 2. I add that to 1. That's negative 1. Negative 2/3 plus 1, negative positive 1/3. 1/3. 0, so that didn't change anything, and then the same thing, so 1/3 again. Okay? Yes?
Can you multiply row 1 by -2, row 2 by 3?
That's almost like doing this. Technically, it's not an elementary row operation, so I probably wouldn't do it that way, although the result might be the same. I'm not sure. Okay, so it looks like since we have 3 equations, we just need to get rid of one more. So let's get rid of this one more. This is a 2, and this is a -1. So I think I just multiply the second row by 2, right? So multiply row 2 by +2, and then add that to row 3, and then we're going to replace row 3. 3, 3, 1, 0, 1, 0, -1, a third 1, and another 1/3. And so now, I already put 2 zeros down there because the first 0 is not going to change, and then now I got this set up so that I would actually get 0 for the second one, so that's done. Now comes the tedious algebra part, right? So this is a 2/3, but I'm adding it to 0, so that's not a big deal. That's 2/3. This is 2 minus 2 is 0, and then this is 2/3 again, added to 1 5/3. Okay, so I'll put my dotted line, maybe just put a straight line, because my dotted line looks like 1s. And that would be confusing. So that's the augmented part. And so at this point, I think I can transfer it back into my system because I'm already in row echelon form. So my bottom triangular zeros, it's all set. And now I just have to solve for this. And I have to solve for this using back substitution. And then we'll see something interesting happen here. This is 3 equations, but we have 4 unknowns here. So let's see what that is going to do for us. So I have 3w. Remember that the first variable is w. Actually, the whole first line didn't change, so I'm just going to call it 3w plus 3x plus y is equal to 1. And then I have a negative x plus 1/3 y plus z is equal to 1/3. By the way, if you don't want to deal with fractions, you could have kept going just a couple more steps and multiply the second row by 3, multiply the third row by 3, wipe out the fractions. But I didn't do that. All right, so the last one, this is my this is my third spot, which is my y. That would be 2/3 y plus 0z is equal to 5/3. Okay? So if I do the back solving, I have a value for y. So I have 2/3 y is equal to 5/3, and if I solve for that, I'm going to get y is equal to 2/5, 5/2. 5/2. Let's box that, since this is potential to get messy and I might lose stuff. Okay, the next equation is minus x plus 1/3 y. And I found a value for y, so I'm going to put parentheses there, and then I want to put the value for y that I found. plus z. Now, did we find a value for z? We didn't find a value for z, did we? So, anyways, I have value 5 halves here for y. I don't have a value for z, which is weird because that's my last variable here. That's the first one I should have solved for, but that didn't come up in my bottom equation. So we have a little bit of an issue here, and the issue is that if I'm back solving, I want to fill in my variables from the bottom to the top, from the last variable to the first variable, and we didn't get a value for z. So what we're going to do is, let's just make this value for z arbitrary. Let's call it t. So t is a parameter that we're going to use. So it looks like we have a solution here, but our solution is going to require us to have a whole bunch of answers. So let's say, instead of saying I'm going to let t equal to 0 or t equal to 5, I'm going to let t equal to just a random variable that I'll call a parameter. And then we'll try to put the solutions together after we're done here. Okay? So now I've made a place value for z. I found a value for y. Let's continue on and solve for x. So I'm going to get minus x. This becomes more fractions, 5, 6. And then now this is the t parameter is equal to 1/3. And I'm really interested in solving for x here because that's my next step. I made t a parameter. I found my y, so now I need to find x. So I'm going to just say x is equal to, I'm going to change all the signs here and bring everything over to the other side. I'll have a t in there somewhere, right? And it will become positive because of the negative sign. And then if I subtract, this is 5 minus 2 is 3, and negative of that is, I think this is going to be 1. 3/3. All right, you guys better check that because I'm just going out on a limb here. Do the algebra on your paper. It's really just arithmetic with fractions. Is it right? I need 2 nods. I got 1 nod. Okay, thank you. I'm right then. And if I'm wrong, it's your fault. We found a value for x. Let's box that. And then now we have one more variable, and that's the w. Let's see what we can do with that. What? Thank you for checking. So negative 1/2. All right. Now, what do we have left? The first equation to solve for w, we have a 3w plus 3x. Now, what's x equal to again? I'll put a parentheses and put my x in there. Plus y. And then there's no z, so I don't have to worry about putting the z's equal to t. By the way, maybe I should have put z equals to t here and put a box around that as well. All right. And this equation is supposed to be equal to to 1. And let me put in those values that I got for y, 5/2, and for x. This has that t parameter, t minus 1/2. Maybe we should have multiplied everything by 3 to wipe it out, huh? Yeah? Plus 1/2 here? Thank you. All right. I want to solve for W. Here's my crazy algebra again that you guys are going to check. W equals I'm going to start off with my parameter t, negative 3t over here, and then everything else, divided by 3, so that's going to be just negative t. Then you guys can figure out what that constant is. So 5/2, subtract negative 3/2, subtract negative 6/2, which is 3 divided by 3. 1. I'm going to go with 1 plus 1. What do you say? You guys are doing this on paper, right? This is an interactive class where you do all the work. I mean, where we do the work together. -1? Oh, so close. I knew that. I was just testing you. Okay. Need 2 nods. Yes? Yes? Yes. All right, moving on. Let's put a box around that. Okay. Well, I think that's it. I got my x, my y, my w, w, x, y, z. So that's all solved for. Let's see. I obviously didn't get just numbers here. If I just got numbers, then I have 1 point that I would be dealing with. So let's see if we can imagine what this would look like. I'm going to write it kind of like in vector form-ish. I'm going to say W is equal to, I'm going to start with a constant. Yeah, you. Minus 4/3? Uh-oh. You good, Daniel? Yeah. All right. Thanks for checking. So, there's a lot of tedious arithmetic here that you guys have to be able to do. I already passed this class, so I don't need to do the tedious arithmetic. Anyways, we're back to writing the solutions. I want to write the solutions. I'm going to write it with a constant first. So I'm going to go -1 minus t for my w. My next variable is x, going in order, and then I'm going to write that as a 1/2 plus t. And then my next variable is a y, and y just happens to be a constant, so I'm just going to write that as 5/2. And then the last one, z, is just going to be a t. So I'm going to write it, you know how we write the system with spaces and stuff. I'll write the t over here. Now, this is my solution, and my solution, x, y, w, x, y, z, is equal to something with t's in it. Now, this is hard to visualize. Let me rephrase that. This is impossible to visualize because we're in 4 dimensions. Okay? So we can't visualize this unless you help your brain out a little bit with some choice chemicals, you know. Anyways, so you can't visualize this, so we could still not see it, but we can still anticipate what this thing would look like. Now, oh, your quiz today. You guys had a quiz, right? Your quiz today, wait, did you guys have a quiz? Yeah, you guys had a quiz. In your quiz today, the first answer that you gave was an equation for a line, and the second answer that you gave was an equation for a plane. What's the difference between those two answers that you gave, if you got it right? The first one had t, and then the second one had s and t. So the first one had one parameter, the second one had two parameters. If you didn't have any parameters, you would be looking at a point. If you have one parameter, you're looking at a line. If you have two parameters, you're looking at a plane. And not in this case, but if another problem gave you three parameters, you'd be looking at a three-dimensional space. We'll talk more about that later. Not necessarily. I'm talking about a whole space. Oh, let's put that off to the side. Okay, let's focus on the idea that one parameter is a line. So in this four-dimensional space that you can't visualize, but maybe you can try to imagine a four-dimensional space. This equation, or this answer, the solution that we have, is a line in four-dimensional space. Okay? That's what it is. Now that you know that, the answers that you guys gave on your quiz had something like a vector plus t times another vector or something like that. It's exactly what we have here. The reason why I wrote it like this is that those numbers without a t, let me write the w, x, y, z first, and let me now write it in vector form. Those numbers without a t can be brought together, kind of corralled together as a vector. That would be a -1, a 1/2, a 5/2, and a 0. So that's one vector plus t times, and then the direction vector for this line in four-dimensional space would be the coefficients of t. I have a -1, a +1, a 0, and then a +1. So this is my solution set. For any value t I choose. Now here's the thing, is that I can give you any value of t, and you punch this out and compute it, and then you put it back into w, x, y, z in the original system, and it better work. If it doesn't work, then we did something wrong. And I know we didn't, because we have all of us thinking together. Right? We're all holding hands and singing linear algebra stuff. So, should we check? I don't want to check. I can go home, write a computer program to check this, but I'm not going to check right now. So, we got it right. Any questions about this? So these, oh yeah. The first one? Those are the coefficients of the t. So that's you take the things that are being multiplied by the t, and then you put them in the vector form, and that's the same thing as what we're doing. Cool? Anything else? All right. That was fun. That was like the whole page. All right. So a couple of definitions, or one definition in a theorem that comes up here is called rank of matrix. We actually should have done the other problem to make this a little bit more interesting, but we did this one. So the rank of a matrix is a number of non-zero rows it has in its row echelon form. So if you reduce everything into row echelon form, then you get your rank. The rank theorem says that if you have n variables in your system, then and your system is consistent, it has solutions, then the number of free variables, which is the number of parameters that we created, so those are the free variables, should equal to the number of variables you have minus the rank. Okay. The first problem that we did was not consistent. It didn't have a solution. I should have asked you about that. But do you guys remember what consistent was? Consistent was you had at least one solution. Could have an infinitely many number of solutions, but you need to have at least one. So we had a contradiction, so it was not consistent. So that particular solution, that particular problem does not apply to this rank theorem. But the problem that we just had ended with a matrix that looked like this. So this is our matrix. And if you remember, if you counted how many variables we had 4 variables. So our n is equal to 4. Our rank is the number of non-zero rows. So we weren't able to eliminate a whole row, make a whole row full of zeros, so we have to count all the rows. So the rank in this case is equal to 3. And then if you look at our solutions, we had a free variable. We had one free variable. And so we can put this into this equation that says that the number of free variables is equal to the number of variables minus the rank. Okay, this would be more interesting if we had a row or two full of zeros, and then you can see how the application works. But this works fine too. Okay, so whenever you do a problem, even if it doesn't ask for the rank or anything like that, you should take a look at what the rank is, and then compare it with the number of variables you started with, and the number of zero or non-zero rows that you have. Okay, questions? All right, let's take a look at the next page over here, which some people had alluded to already. Wing Zhang, I think, brought it up once the first time, where when you're doing the row echelon form, make everything else 0 and everything else 1, and then this is called a reduced row echelon form. So in a reduced row echelon form, first of all, you have to have it in echelon form, so it has those steps. And then you need a couple more steps to make sure it's all cleared up. The leading entry in each row is 1, and in each column containing a leading 1, you have zeros everywhere else. And then the process of going all the way to the reduced row echelon form is called the Gaussian or Gauss-Jordan elimination. So let's take our echelon form from the previous problem. Let's continue working on this and have it reduced row echelon, just to see what the steps are to reduce it all the way. Shall we? It's going to require a few more elementary row operations, but by this time, the elementary row operations are going to be the simpler ones. It's a second type where we just have to make sure it's 1. The leading coefficients are 1. And so in doing that, I'm going to do a couple of row row operations in one step, and then we'll see how this works out. So to get it to reduce row echelon form, the first row, I think I want to multiply that by a third, the whole thing, right? So I'm going to take 1/3 times the first row, and then I'm going to replace that first row by whatever I get. So that's the second type of row echelon, the elementary row operation. The second one, I will take the second row, multiply it by -1, and replace that row by that. So basically just multiply the whole second row by -1. And then I'm going to take the third row, and I'm going to multiply that by 3/2, I think is what I want. So I'm going to do all this in one step. So the first one is going to be a 1, 1, 1/3, 0, and 1/3. Is that right? The second one just changes the signs. 1, -1/3, -1, -1/3. And then the last one is going to make this 3/2. This doesn't change, and this multiplied by 3/2 is 5/2. So some of these numbers might look familiar. Are we in reduced row echelon form? So it's in row echelon form. The leading entries look like they're 1. Oh, each column containing a leading entry has zeros everywhere else. I want this to be 0. I want this and this to be 0. Okay? So let's do a couple more elementary row operations to wipe that out. I could do that. Yeah, then we can multiply by 2 again. Or we can just, so once you have the leading ones, then you can kind of backtrack. Let's say you want to get rid of this 1/3. So I'm going to take the third row and multiply it by positive 1/3, and then add it to the second row, and then replace the second row by that. So it's pretty systematic. If you do this systematically, then you can solve for it, as straightforward as possible. You could also do it non-systematically, in which case you might have to erase a mistake, or not a mistake, but erase a change that you made. Yeah, you could do that. See, but by doing it this way, though, I'm kind of guaranteed not to change the ones, because anything below that is 0. So I'm also going to, at the same time, get rid of this 1/3 here. So I'm going to take the same row 3 and multiply that by -1/3, and then add that to row 1, and then replace row 1 by that. So I didn't change the last row, but I will change the second row. And the first 2 is not going to change because there's 0 contribution. Now this is going to be 0. This is going to be -1, and this is going to be 1/2. And then now I have a 1, 0. Oh, that's not a 0 yet. 1, 1, 0. And this is 0 and 0, so that didn't change. And this is -1/3 plus this. What? Come on, we have 2 minutes. Help me. So -1/3. This is going to be -5/6. -5/6 plus 1/3 is what? -7/6? Are we done? No, we're not done yet. Because this is still not 0. So multiply the second row by -1, add it to the first row, replace the first row. 1, 0, 0. Oh, this is going to come back to -1. 0, 1, 0, -1, 0, 0, 1, 0, and then I'm just going to put star there. Is this a reduced row echelon? Let's look at the definition. Number 1. Right. So number 1, it's in row echelon form. Yes, check. Number 2, the leading entries are 1. Yes, check. Number 3, for any of these leading entries that are 1, everything else in that column is 0. Does this have a leading entry of 1? So we don't count that. So yes, each column containing a leading 1, each column containing a leading 1 has zeros everywhere else. This does not contain a leading 1. I have 3 leading 1s over here, so I'm looking at 3 columns that have zeros everywhere else. So yes, this is a reduced row echelon form. And I'll tell you what this number is? That number is 1. All right. See you guys next time. Is there a quiz next time? No.